Hi guys, welcome back to my Case of Econ Struggles. Today I'm going to keep talking about econometrics, and today I'm going to start talking about standard errors in terms of regressions. So as usual, timestamps are below if you would like to jump around, but let's go ahead and get right into it. So once again, unsurprisingly, I'm going to keep talking about the regression where we regress stress level and number of cats. If you want me to start talking about a different example, please feel free to suggest one in the comments below. And if you see one that you like, make sure to like that comment. I will basically start using the example which got the most likes when I start making that video. But for now, we're going to keep talking about regressing the stress level and number of cats. So in Stata, if I were to look at my Stata output, I might see something like this, where I've got my dependent variable here. This is my independent variable number of cats. Here's my constant. I've got a coefficient, and I've got a standard error, and then I have a t-stat, a p-value, and a confidence interval. And today when I'm talking about standard errors, I really want to talk about this box, this standard error box. I want to talk about what exactly the standard error is, and I want to talk about how it's calculated. So in the last video, I talked about properties of estimators, and one property I talked about was the variance of beta hat, where we know that beta hat is our estimator, and beta hat is also sort of the estimate that we get in a particular sample. But I'm not really concerned about the beta hat in our estimate. When I talk about standard errors, I'm talking about, well, what is the variance of beta hat over all possible samples? But of course, we're going to estimate that standard error using the sample we have. And in order to calculate that based on the sample we have, we're going to remember that our beta hat in matrix notation is x transpose x inverse times x transpose y. Again, I'm talking about matrix notation. And I know that the variance of epsilon in a particular sample is just sigma squared times epsilon. Now, if I want to think about the variance of x for a second, or n times the variance of x, I'm going to claim to you that x transpose x is just n times the variance of x. And so then if I want to think about the variance of beta hat, what I could do is I could just take the variance in my epsilon term and divide it by n times the variance of x. What I would get is I would get sigma squared epsilon over x transpose times x, or x transpose x minus 1 times sigma squared epsilon. This right here, this is going to be the variance of beta hat. And when I take the square root of that, that's going to be my standard error. Okay, so a natural question is sort of, I made this claim that x transpose x is n times the variance of x. And so now I want to sort of show that intuitively. The way I'm going to show that is I'm going to take this example with cats and their weight from before. The only difference, to make this a little easier on myself, is I'm going to take the d-mean version. The mean of the weight of cats in my sample is equal to 10. And so if I d-mean it, this is going to be 0, 0, 0, 0. This is 5 pounds over the mean. This is 5 pounds under the mean. And now what I'm going to do is I'm going to call that variable z, or matrix z, for a second, which means that z transpose z is just this row times this column, which is equal to 50, which is exactly equal to the variance of x that we calculated sort of in that first video on statistics. And so if I have a d-meaned, then this whole ztz is going to be the variance of z. And if it's not d-meaned, you can show that if it's not d-meaned, you're going to get n times the variance of x. Okay, so just going back to standard errors, now what we're saying is the variance of beta hat is 1 over n times variance of epsilon over variance of x, which is just variance of epsilon times 1 over n variance of x, which is xtx minus 1. So this whole thing is going to be inverted times sigma squared epsilon. And now if my n goes to infinity, then this variance of beta hat is going to go to 0 because I have an n right here in the denominator. So it's going to converge in probability to 0, which means, based on the last video, that we have a consistent estimator and beta hat is consistent. And that means that if I have my Gauss-Markov assumptions, and I assume that sigma squared epsilon is normal, then what I'm going to see is I'm going to see that beta hat is going to be what we call blue, or a best linear unbiased estimator, because we can show, and I'll show this in the next video, that beta hat is going to be distributed normally with a mean of beta, or an expected value of beta, and variance xtx minus 1 sigma squared epsilon. It's going to be our estimator with the lowest variance. It's going to be consistent. It's going to be unbiased. And I'll show sort of the derivation of why OLS is blue in the next video, or in the next couple of videos. Okay, one thing I want to talk about real quick with standard errors is this idea of homoskedasticity, which I talked about in the Gauss-Markov assumptions. And so we assumed that the variance of epsilon, or sigma squared epsilon, was constant across values of x. And that means that was part of the reason, that was part of those GMA assumptions that led us to believe that beta hat was blue, or a best linear unbiased estimator, and that it was consistent. But what happens to these properties of beta hat if we no longer have homoskedasticity, if the variance of epsilon or if sigma squared epsilon is not constant across values of our independent variables, well, I'm going to show you that it's still going to be unbiased, but it's not going to be consistent. We're not going to have consistency in our estimator, and so our OLS will no longer be blue. So what I'm going to start doing as we get more and more into this is I'm going to talk exactly about what I mean with the OLS being blue, that it's unbiased, that it has the lowest variance, and that it's consistent. And then as we get further along into our understanding of standard errors, I'll talk about heteroskedastic standard errors and what we can do in order to sort of fix this issue of heteroskedasticity. But if this video or these videos in general are helping you out, please like and subscribe. We'll see you next time for another case of econ struggles.